Hello everyone. Today we will see Module 5 in Machine Learning course. There are 3 chapters in Module 5. They are Evaluating Hypothesis, Instance-Based Learning, Reinforcement Learning. Let us see what we mean by evaluating hypothesis. It is necessary to know the accuracy of the hypothesis once we find out the final results in machine learning. We may want to know what is the value of accuracy for the given model. We will find out the statistical methods for finding out the hypothesis accuracy, and this will done based on 3 questions. The first question is, suppose that we have found out the accuracy of the model considering a small data set. Means the data set is limited. Now, if we find out the accuracy for many more data sets for the same model, then what will be the effect of this on the accuracy? Will the accuracy will increase or decrease, or remains same, or even remains unaltered? Second question is, suppose that for the additional data sets or for similar data set, if the model outperforms, means the accuracy obtained is good, then will this continue for the other data sets also? What is the probability that we will get the same or better accuracy for other data sets also? The third question is, suppose that we don't have large enough data set which will cover all the aspects of the class and attributes. Suppose that our data set is small, then what is the best way to use this data set for calculating the hypothesis and further calculating the accuracy? Usually, it is known fact that limited data may misinterpret the class, or it may not represent the entire training space. It may mislead the model to arrive at wrong classification or wrong predictions. Usually, statistical methods helps us to find out the difference in accuracies. Accuracy found from the model and actual scenario. There may be assumptions associated with statistical methods, but definitely with the help of statistical methods, we can easily find what is the difference in model result and actual result. Hence, evaluation using statistical methods is a must. Motivation. We cannot trust blindly the learned hypothesis. There may be critical situations like predicting whether the patient is having heart disease or not, or whether the patient is having cancer or not, etc. Wrong results may mislead the authority to take wrong decisions. Hence, it is very important to evaluate the performance of the model and performance of the hypothesis. This need to be done very precisely so that we make sure that the results of the hypothesis is promising. Once we are sure that the hypothesis results are promising, we can use the hypothesis for many cases. Results of the hypothesis will tells us as whether to use it or not. In case of medical treatments, it is advisable to have as many samples as possible. But if the dataset size is limited, we may first need to know what is the accuracy of the learned hypothesis. Based on this, we may choose to proceed further or use another model. Usually, evaluation of the hypothesis is integral part of many learning methods. Without this, we cannot imagine or trust the model at all. For example, consider decision tree example. It is necessary in decision tree that we need to find out the impact of pruning on the accuracy, which will reduce the overfitting problem. As we know, pruning is a data compression technique in machine learning and search algorithms that reduces the size of decision trees by removing sections of the tree that are non-critical and redundant to classify instances. If we find out the impact of this pruning on accuracy, we may decide whether a particular pruning step is beneficial or non-beneficial. It will also avoid overfitting. Overfitting means our model overfit to our data set that is used for training and testing and give us high accuracy, but it doesn't have good outcome for the other data set. In short, a decision tree is overfitted if it gives high accurate output on training data but low accurate output on testing data. Therefore, it is important to know the accuracy of the pruned and unpruned decision tree to find out likely errors. If the data set is large enough and if it covers all the aspects, then it is straightforward to calculate the accuracy of the hypothesis. The same thing becomes tedious if all the data is limited or when we want to find out the future hypothesis accuracy, and we must learn the hypothesis and calculate its accuracy. The difficulty arised are either bias in the estimate or variance in the estimate. Let us see what is bias in the estimate. It is noticed that if the accuracy of the hypothesis is very good, then it is likely that the accuracy will be reduced for future examples. This happens when the hypothesis space is very rich and the model seen all the possible hypotheses already, means model is gone through or studied or learned all the examples which are very vast. This will eventually overfit the training examples. To solve this problem and to get the unbiased future accuracy, the hypothesis is tested on examples which are not there in the training data set. Variance in the estimate. The goal of supervised machine learning algorithms is to estimate the mapping function for the output variable given the input data. The mapping function, usually denoted as small f, the output variable is usually denoted as capital Y, and the input data is denoted as capital X. We call this equation as y is equal to f of x. F will indicate the function which will transform the input to the output. The mapping function is often called as target function, given that it represents a function that is a given supervised machine learning algorithm aims to approximate. The prediction error for any machine learning algorithm can be broken down into so-called as bias error and variance error. Variance is the amount that the estimate of the target function will change if different training data are used. The target function is estimated from the training data by a machine learning algorithm so that we should expect the algorithm to have some variance. In ideal scenario, it would not change too much from one training data set to the next training data set, meaning that the algorithm is good at picking out the hidden underlying mapping between the inputs and the output variables. Algorithms that display high variance are influenced by the specifics of the training data. That is, specifics of the training influence the number and types of parameters used to characterize the mapping function. Low variance suggests small changes to the estimate of the target function with changes to the training data set, whereas high variance indicates large changes to the estimate of the target function with changes to the training data set. In general, non-parametric machine learning algorithms that have lot of flexibility also display high variance. Supervised machine learning algorithms should reach for a low bias and low variance. In turn, the algorithm should achieve good predictive performance. Variance actually measures the variability of the model prediction if we would retain the model multiple times on different subsets of the data. To gain an clear idea about variance, we will consider an example. Suppose that we have 100 training examples in our data set. Actually, 150 examples are in total, where 50 examples are reserved for a 50-50 split between the validation and testing, that is training and testing. Now we pick up A specific example from this set of 150 examples. Suppose that this specific example is xi. We are required to classify this xi in any one of the classes k1, k2, k3 up to kn. Means xi should go to one of these classes from k1 to kn. Now randomly pick 100 samples from our original set of 150 samples, excluding the one which already picked, that is excluding our xi. Now suppose that we choose a hypothesis that has many higher degree terms. For example, a1 into x raised to 8 plus a2 into x raised to 7 and so on, and do not regularize it. We don't want to regularize it. It will fit the model very nicely and we get a low error on our training set. Now, run the same model on the randomly chosen sample which we have taken earlier, that is xi, and it predicts wrongly. We repeat the above process of having 100 samples 5 times, and each time we will get different results. Say it may be classified to KA or KB or KC, KD and KE. This variability in our prediction implies our model is overfitting the data which is given. That's why it is not able to follow a general pattern in our data and is being affected by outliers more than it should. Estimating the hypothesis accuracy. Machine learning models will give us the end results as hypothesis. We may obtain many hypotheses which we call as hypothesis space. The hypothesis which we select finally is called as target hypothesis. Since there are many hypotheses, we are interested in estimating or calculating the accuracy of the hypothesis. If we get the expected hypothesis, then we trust that hypothesis and classify the test samples. We are also interested to know and calculate the error associated with the calculated accuracy. Knowing the errors will help us to take appropriate actions to rectify them, like back propagation, changing the weights, checking the inputs, etc. We will make some assumptions. Some training samples out of all training space are such that our target function can be defined over them. What we mean by target function? Target function are one which convert the given input to the expected output. Notice that there may be many functions which can do this job, but the one which we select will become the target function. Our assumption is that the target function is applicable to some of the training samples. Example, people. People in the sense, people are taken as training sample and the target function is whether they will purchase new skis or not. As you know, ski is a sports equipment as shown in the diagram. We assume that there exist some people in our data set who will definitely purchase the new skis. We further assume that there are samples in sample space or instance space which are available at different interval of time, that is at different frequencies. Assume that there is some probability distribution capital D which will define these frequencies, that is there is more probability of getting instance which will purchase new skis rather than not purchasing it. It doesn't mean that the instances will have only samples which will purchase new skis, but it will indicate that there exists some probability that people are there who will purchase the new skis. Note that D will never says the instances will only positive or only negative. Both cases may be possible. It only determines that there are some instances small s which will purchase these keys and they are present. What is the learning task? The learning task is to learn the target function f out of all functions and considering all the hypotheses, that is hypothesis space capital H. The training examples are drawn independently or randomly and it is given to the model to classify it. Now, to illustrate, we will consider the target function as people who plan to purchase new pair of skis this year. The training data is people survey report. This report forms as data which is actually a survey made on people when they arrive at a ski resort. As we know, any training data contains attribute name and attribute values. Values are usually numerical values. In our case, the attribute names are age of the people, their occupation, last year how many times they skied, etc. Here capital D is the distribution which will indicate whether the person X will buy the ski or not. It is indicated as 0 or 1. So the target function is f colon x plus inside flower bracket 0 comma 1. This target function will classify the people as whether they will buy ski or not. If yes, then 1 is assigned. If no, then 0 will be assigned. So far, we have discussed about the assumptions and settings in the model. Now, let us know what is our main interest. That is, what we want to find out. First one is to find out the hypothesis. If there are more number of hypotheses, then we are interested to calculate the accuracy of the hypothesis. We would like to consider the hypothesis which will give us the best accuracy. Second one is we want to find out what is the probable error in this accuracy estimate. Sample error and true error. What do we mean by error in accuracy? How to find it? If you see carefully, there are two notations in this. One is accuracy and the other one is error. The first one is error rate of the prediction or hypothesis over the entire sample of data, that is in training data. The second one is error. Error rate of the prediction over the entire space or distribution. We may have taken small amount of data or sample data only for the prediction or for the classification. The error in this is called as sample error. The error present in complete space of data is called as true error. Obviously, sample error will be a fraction of the entire space. We will define the sample error. The sample error, usually denoted as error of h with subscript s, of hypothesis small h with respect to the target function f and data sample capital S, is error of h is equal to 1 upon n summation of delta f of x comma h of x over all the samples x belonging to the sample space capital S. Here small n is the number of examples in capital S and the quantity delta of f of x comma h of x is 1 if f of x is not equal to h of x and 0 otherwise. The true error of a hypothesis is the probability that it will misclassify a single randomly drawn instance from the distribution capital D. The true error is defined as true error of hypothesis H with respect to the target function f and distribution capital D is the probability that H will misclassify an instance drawn at random according to the capital D. It is denoted as error of H is equal to probability, that is we denote it as PR, of f of x not equal to h of x for all samples belonging to the distribution D. Here the notation PR x belonging to D indicates that the probability is taken over the instance distribution capital D. What we usually wish to know is the true error of the hypothesis, because this is the error we can expect when applying the hypothesis to the future examples. All we can measure is the sample error of the hypothesis for the data sample S that we happen to have in hand.